Okay, welcome everybody. This is our workshop on T-ray nanometrology and T-ray related measurements, imaging, spectroscopy workshop. This is a series that we should finish in a few sessions. And at the end of the session, then we can review and have some projects of individual participants. So what we have done from before, do you have any question at this point?
Yes. We spoke about sample preparation. The sample preparation looks simple. What issues arise in daily use with this tool?
Right, very good question. And we will have an example probably today. We'll have many examples, but at least one example maybe today, how we solve a real world problem with this approach. So to answer your question, the instruments, they keep running, so to speak. There's no consumable for the instrument. It's all software. And they are all software all installed. And I will go through all of them today. So issues could be, one issues could be that computer may go down. You know, this software run on Windows PC, and Windows came a long way. Now they are very stable. And the machines, when they are installed elsewhere, there are 2 years of warranty on it. So we have seen that people have been running, using this machine for many, many years without any difficulty of the hardware itself. But only problem they had is computer either was not maintained or whatever happened, computer gave up. So after 5-6 years, computer requires maintenance. There may be software updates now and then, which is not a big deal, but the terahertz source, after 6-7 years, probably it's better to have a new terahertz source installed. But that depends on how much it's used up. Those are the main technicalities. Any more point? Okay, so let's move on. You know, some of this issue will come here in today's session. So in past, we have outlined the rationale, the source, the instrument. We'll go through a little bit more of those today as well. But practical examples will come as well. Maybe not all of those today, but they will. And here are some of the examples of the images. On the upper left, Lumina, 50 nanometer by 50 nanometer by 50 nanometer cube. Then the gold nanoparticles, then carbon nanotubes, which are aligned at an angle, because carbon nanotubes, when they are aligned at an angle, they serve as a filter, polarization control. All of those things can happen. The upper right corner is the 200 millimeter patterned wafer that has all those die. And those dies are, cut, separate, electrode, attached, and then they become a chip, packaged, and then they become a chip. The lower left corner is a drop of nanocellulose dried at room temperature. And then a few layers of image of some other sample. Nanosuspension, which is nanoparticles in suspension. The red one, and the rightmost one, the gallium nitride, lattice damage. Many of those things will be, taken on its own at a later time. But today, first, let me give you an outline of how the instrument organization look like. So tabletop system, it has three main components. The first one is the main box, and then the nanoscanner, which has X, Y, and Z, and optionally a theta axis, sometimes, not always. And of course, the computer and the software that runs everything. So if you look at this diagram here, A is the main box, and then B next to it is the XYZ axis nanoscanner. And then there are digitizers, and there are pump lasers, driver. There are, of course, the PC and the monitor. So the connections are, shown this way. You'll see that COM3 here we have taken out, because RS-232 used to be a way of connecting the scanners. And now we use the USB, which is a faster and better connection. So this, this is all kind of beyond the user. They don't have to do anything, because when we take a system to somebody's facility, we install it, and we train them for operation. So here is a, this little beaker here with liquid, because there are two modes. This is the nanoscanner, when holds its sample, is measured in the transmission mode. Measured in the reflection mode. But we can use directly in front of the beam and measure in the transmission mode as well. And you'll see those coming later. Software required. All the software that are required to run this machine are pre-installed. So it's a complete system that is delivered. We use a platform called V. It stands for Virtual Experimental Environment. This is a platform marketed by Keysight, which actually started long time ago by HP. HP then split into Agilent, and then Agilent had that software, and now Agilent has split into Keysight and Agilent. So Keysight deals with this kind of software as well as some hardware, digitizer, all of those. So we exclusively use this platform. It has a lot of advantage. It has MATLAB built in, Excel built in. It has its own library, very well developed library. It has .NET. So it's quite a bit of thing that comes with this platform. And any development project can take advantage of all of them without paying extra. And then we have developed quite a few apps for running under the V platform. And Microsoft Excel, a lot of time used for simple graphing, but A lot of time graphing are very complex, so we have other software to deal with them. For example, Excel can handle with only 1 million data point, 1 million rows, not data point, 1 million rows. You may have so many different columns, but for our purposes, a lot of time that's not enough. We may have 1 billion row need. Because, and as you will see, or more, as you will see, because this data are image, right? Data is converted to image. But sometimes we want to manipulate the data too. Particularly, we have been thinking of machine learning capabilities. So, but we still use Excel for, simple graphing purposes. And of course, Microsoft Word is very useful for writing reports. And there's a third-party software, it's called Voxler. That's for three-dimensional image generation, manipulation, and all of those things. And there's a public domain software called ImageJ. And we use that for quantitative measurements. And if you end up doing a project, I will encourage you to install one of this software. This is public domain, ImageJ. And that way you can do something hands-on. So apps are, there are quite a few apps. They look something like this. For example, leftmost one is app for homing and positioning of the nanoscanner. When you run this, it tells the current position of all the scanners. But then you also can home them, meaning reset, everything start from the beginning. And then you can instruct them to go to a given position. That's the only thing this app does. The other one here is called the find the X scan limit. Because there are 3 different axes, so if a sample is mounted, then we need to know from where to where scan on the X-axis, where to where scan from on the Y-axis, as well as on the Z-axis. So there are 3 different apps for each axis to determine the extent of the scan. For example, here you see the profile goes up, and then this is the profile of the sample, and then no more sample here. So now we can choose by the markers, we can pick up the position that we are interested in. For example, we can scan the whole thing. This is a wafer, which is 150 millimeter. So we can now know where to start and where to end to get the whole wafer. Or if we choose to, look at some feature, then we can bring the marker at that place, and this position will tell us from where to where on the X-axis. Similarly, there is Y-axis and Z-axis, and everything is then goes into this front-end piece, which you call as the main scanner. So it has the, a data file name, start position, end position of the X-axis, how fast to scan, how fast to return back, and few other things. So these boxes are populated by the user, as well as the other 2 axes, the Y-axis and Z-axis. The main thing in the Y and Z-axis is the start point, end point, and step size. Similarly, in the Z-axis, start point, end point, and the step size. Once this is done, and then the file name is given, then all you have to do is hit the run button and it will keep running. Then all the BLR metrics will go in this data file that you have named, whatever you have named. And when the scanning is done, then other software takes over and creates the image. So for a whole wafer, this is the profile, how it looks like for the whole wafer when all this scanning is done. As you can see here, we scan from 0 to 200 millimeter on the x-axis, from 0 to 200 millimeter on the y-axis, and on z-axis, nothing. It's only one surface scan. So this profile for the entire wafer, then with all this intensity are saved in a data file called BLR matrix. And then as the next step, you can do quite a few things. So here, one of the example is, this is a sample that's mounted on the nanoscanner, which is a smaller scanner. It's about 100 millimeter by 100 millimeter by 25 millimeter depth. And this sample over this disk is the sample. Can you make a guess what it could be?
Nickel.
It's actually the platter of a hard disk drive.
Oh.
You see this donut?
So this would be silicon then.
I'm sorry?
This disk is silicon. If
No, this is the hard disk platter is not silicon, by the way. So those are magnetic material. Those are very special proprietary material. We would not know.
I know the writer is a magnesium
This
writer.
one was the silicon wafer, having all the patterns. But this example is a different sample. All right. So again, you see the BLR matrix profile looks like this. But then when you make the image, that's how the platter image look like. A little defect here, a little defect here, they become visible. The surface, you see, this is shiny surface, very smooth, shiny surface. Nonetheless, when you take a profile along this line over here, you see the surface roughness. And then you can quantify the surface roughness. You can measure the surface roughness. So that's just an example that what kind of applications we can have in this machine. Here is another thing, the image resolution. Once the measurement is done, so the measurement has a scanning resolution. That's one factor that determines the scanning, image resolution, but also when the software manipulates that BLR matrix, has some option to control the image resolution. We can make a grid of, let's say, 50 by 50, and that will give us an image almost immediately. But some details may, hurt. Probably not all the details will show. On the other hand, you can keep increasing the resolution gridding size. And here you have the scale. All other scales have been suppressed, but only one scale has been here to show these, how big these things are. These are 4 by 5 millimeter, 4 millimeter by 5 millimeter. And if you look really closely, you will see that the highest resolution, 2000 by 2000, has a little bit more storytelling compared to rough resolution. For this image, for this sample, it was not very critical. But for some other sample, difference will be remarkable. But this shows that even with the, fast gridding time, you still can get a decent image. It's almost like, if you have a camera, you can change the, for example, you can change the, in your camera, you can change the, pixel size and everything, right? So it's almost like that. Similar kind of capability. I don't know why this thing is not doing right. Okay, here we go. Next, here is another example of measuring the lattice parameters. Now, this is not a very scientific sample. This is a seashell, which is nature-made sample. The seashells have a lot of importance, a lot of curiosity, scientific curiosity, as well as application. The seashell effect. And I will share some of my thoughts in a white paper I wrote. But what we did is try to measure, because seashell is calcium carbonate for most part. The shell is very hard because of that calcium carbonate. So if it is the calcium carbonate, can we see its lattice structure? That was the question. So, what we have done here is you can iterate, but then we have this image in volume that shows some kind of crystal structure here, some other kind here, some other kind here, some other kind here, and different kind here. There are 4 or 5 different kind of lattice separation. And they are varying, they're not the same everywhere. And this makes sense because nature is good at doing manipulation on this scale. So, the seashell effect is one of the things that we utilize for example, the sonar and that kind of sensors are made based on the seashell effect. So there are other applications I described, in a newsletter. I will share that with you. So now, if you take only one surface of this is a volume image, we can take any surface, or you can slice through it. Then we can identify the bands where the crystal structures can be measured. And we have just done that. So we have taken A, B, this way, A, B, C, F, and G. So A, B, C, F, and G. Rest of them are not, for example, here is not very crystalline. It's kind of amorphous. And so is this. So is the other bands. So it looks like the alternate bands of crystalline and amorphous structure. So I say nature loves impurity. There are a lot of impurities, and that makes either it is crystalline or non-crystalline. So if we do the graphical analysis of cell layer A, you see these line structures are causing this the variation, the pattern that we're getting here. And the line is given by the separation or width. There is a technique called full width at half maximum. That is the technique normally used to measure the line width from this kind of graphical analysis. I should have said that here, full width at half maximum. If we do that full width at half maximum, then we get average distance between these lines, or lattice parameters, they call it, is 3.17 nanometer with standard deviation of 0.06. And you see they are changing all the way. The G band is very wide. 8.79 with a standard deviation of almost 1 nanometer. So this is a tool now, as you can see, it's not just the imaging and looking at it. This is a tool that allows us to measure the lattice parameter when we can do the right imaging. And this is what we call nanometrology, meaning measurement of nanoscale or sub-nanoscale features. There is another problem, a practical problem. This is the paper I shared with you by email. What is it? Is that these are the little rods. On this rod, there are several layers. First of all, the inner core is the substrate, which is made from alumina. Then they have a copper cladding around that alumina, they call it electrode. Then they have electrode insulator, which is another layer of alumina. And then finally on the skin, they have nickel. So these 4 layers are making some kind of a device that, that this system is for. Our objective was that, first of all, you see the separation between the nickel layer, the alumina again, and then the copper, and down over here, alumina again. So the metal insulator, 4 layers. And these are all made in a way they call spray pyrolysis, meaning that or spray deposition. They melt the metal. The alumina don't need to be, sprayed because alumina wouldn't melt so easily, but somehow they put the cladding layer that way. And then again, they spray the hot metal, the liquid metal, in a controlled way, and then they form the skin. So how the arrangement is the nickel, pure nickel, or thing called lattice dilation. If there is lattice dilation, can we detect it and can we quantify it? This is the kind of problem that this was a project that we looked at. So first of all, if we focus on the surface, their surface morphology for the 4 different samples are different. These samples numbered not by us, but by the manufacturer, 77, 81, 129, and 111. What it differs is that, you see, if there is an electrode here, and there is alumina in the middle, and there is nickel here, then you can apply a voltage, between the 2 metals, and something is supposed to happen. But then also, they varied the voltage between the electrode and the nickel skin. It's not always the same. That's where these numbers are different. Each of these numbers had different voltage applied, each of these samples. And we explored those. So first of all, this skin image is coarse image, but they are different. They're looking different because the 77 is unactivated. So this is how azimuth, then 81, 122, and 111 had different applied voltage. So objective here is to see if there is any lattice dilation. Because lattice dilation meaning that the original lattice expands, and that's where the failure starts. It's called embrittlement. Metal suffers from embrittlement and failure happens, but it starts at the lattice. Because if the lattice expands, that's where the crack, everything starts. So this is a study of lattice dilation of nickel, spray deposited nickel. So first, what we did is we took a pure piece of nickel and measured its lattice to get a calibrated start. So, lattice has a, the nickel has a reported lattice of 3.53 angstrom, 3.52 angstrom. So we got very close to that. So we assumed that this technique is working. And so we took this pure nickel, we scanned over a volume, then one surface was separated and zoomed in, and the lattice parameters were measured. The same way as I showed before. Now, the fun part. Fun part is that those 4 samples, 77, 81, 129, and 111, had varied amount of electrical stress put on them. So if we take 200 micron, 250 micron by 250 micron area, where are we taking from? Over here, you see that? In this rod was polished in an oblique angle so that the layers are exposed. And these layers, I don't know if you can see it clearly, these are the layers that we then focus the beam on. As you can see, it's at an angle, not pure vertical, right? The reason it's at an angle, mounted at an angle, so that the beam is vertically incident on those layers. So first, you can focus the beam on the nickel layer, on the alumina layer, on the copper layer, and you can measure them. So what we did is we measured the interface between the copper and alumina. That's where the beam was focused, and this image were taken. So you can see that the ceramic rich area and nickel rich area was first identified. If you see more crystalline-like structure, that would be metal rich area. If you see less crystalline structure, more amorphous, then that will be the ceramic rich area. And this is right at the interface. So then, because you see this is in real coordinates. The advantage of that, then we can focus, we can move the focal point anywhere and do fine scan there. So this is a moderately fine scan or coarse scan, as you want to call it. And these images were then first generated, and area were chosen where to zoom further. Then when we zoomed on and we scanned, high resolution scanning. So this is 1 cubic micron of all 4 of them. And that shows if you have an inclusion, here there is a particle, alumina particle, that's where the bending has happened. All the lattice got bent. This is a clear inclusion here, over there, and a little bit you can make out here and here. So because at the interface, even though we wanted to look at pure nickel, but you also captured that alumina particles got trapped in the metal, right? It's very useful information. And then this 1 cubic micron are further zoomed in suitable places so that the the inclusions are eliminated, not taken, because we want to see the lattice dilation. If the nickel lattice maintained its lattice plane separation or not. So we further zoomed on 100 cubic nanometer volume and make sure that there is no alumina present in these images. Once we do that, then we take one surface at a time and then measure the lattice parameter. I'm going through all the details so that you get the picture how a real problem is solved by this instrument. And then these lattice parameters, are measured. You see that this line over here is what you call cursor, produces this pattern. And then the full width at half maximum is measured. That gives us the separation between two lattice planes. So we did for 77, 81, 129, 111. What do we get? Pure nickel, we saw that it is 0.353 nanometer or 3.53 angstrom. And then on 77, we measured so many planes, average, it's 0.4465 nanometers. So quite a bit bigger than the pure metal. Lattice has expanded because of spray deposition on alumina. And then when they put the electrical stress, the lowest one is 0.481, a little bit more and a little bit more. Because of higher stress, lattice separation or dilation has happened. And because of that, you can calculate the density. Metallic nickel has a density of 8.863 gram per cubic centimeter. But because of this lattice dilation, the density has decreased. Higher the electric stress, lower the density. So these are very important calculations that comes useful in not only in this case, but in many, many other cases that can be done with this instrument. So other imaging examples for metrology. So probably I think it's a good place to take a segue and ask any questions or any thoughts you have. At the same time, I'm hoping that we're also getting idea for you to do an independent project down the road.
No questions here. It was
Yeah.
very informative.
Please, no question today, but I hope you have followed the steps that how we go about taking a thing over here, this rod structure, and then we go step by step to determine the lattice dilation.
What is the time delay between each resolution? Maybe the first resolution took 4 hours.
So there are two different measurements. First off, these measurements are done just to see how they look like, right? The alumina, the nickel on the skin. I mean, these colors are pseudo colors. You can have different kind of colors. And then we chose at the interface 250 micron by 250 micron area, not volume area, to get a sense of the interface area, because we want to find a spot where more nickel so that we can measure the nickel lattice. Once we have done that, so we have identified that nickel-rich area, nickel-rich area, nickel-rich area. When we have done that, then we did this, high-resolution measurement. So this is a coarse measurement. It takes less time to do the measurement. This is a high-resolution measurement. This is the only one measured. It's only from one measure you can do a lot of things. You don't have to. This measurement and this measurement are not separate ones.
Okay.
Only one high-resolution measurement for each. From there, you can zoom on in anywhere you want. So I have zoomed on from this image. I have zoomed on here to 100 cubic nanometer. I mean, 100 nanometer by 100 nanometer by 100 nanometer. So that I can choose, I can see first if, the lattice irregularities, if there are, and then I take, you see this, the bottom images, one surface of them are taken here. This is a surface from the bottom image, one of them. And now, by this technique, we can measure the lattice separation. So this is the whole procedure, and then the calculation. Yeah.
Looks good.
Wonderful. So I think let's stop here today. Farin has not been able to join. She was traveling, and Dr. Majumdar has some procedures. He was hoping to be able to join. But, important thing is that if probably Dr. Majumdar is not going to be called in to do something, but if somebody else calls and asks Miles that, can you help us with this thing? So hopefully you're getting ready for that.
Yeah. The first question about issues with daily use were resolved with the presentation. It was helpful.
So say that again.
The original question at the beginning was, sample preparation is easy. What were daily issues with the instrument? That question was answered very well. Thank you.
Yeah, so you realize that, I mean, there are some sample preparation, but for example, for wafers, there is no sample preparation. Here we had to polish, we had to obliquely polish this sample to expose the layers. We didn't have to. We could image all of them without polishing because T-ray can penetrate, but we didn't want to take any chance because of this metal. Because metal is a significant barrier for getting in and out. So even though it could go all the way to the copper, but we wanted to see the interface more clearly.
Yeah.
And that's the reason we had to polish it. And also because this was a project from another research organization. So we worked in discussion with them. But other than that, other example, for example, let's see what will come. There will be a lot of other examples where you'll see we didn't have to do anything with the sample, we just mounted on the nanoscanner. Now, for maintaining the machines, again, I said only computer that needs maintenance. The source can run, non-stop as long as it is needed for an experiment, which can be a month or even longer. But a lot of times it doesn't take that long. Whole wafer scanning may take 1 or 2 days, but the machine can run much, much longer than non-stop with very high stability. So maybe as we go through other examples, it will come more apparent to you, or you will have probably other questions.
The software seems very capable. Yeah.
And yeah, and next time what I will do, I will run an example of how we generate the image from data to image. So I'll run their software so that you can see it.
Real quick, originally, was it Keysight Technologies, or did you start somewhere else with C or Visual Basic or something like that? Was it always Keysight and ImageJ?
You mean software-wise?
Yeah.
No, we have always done with this V. It was never, we didn't develop in any other platform or software. It's a the V is, we find it convenient. And it's moderately expensive. It's not very expensive. So when you want to sell a system, you want to integrate all this software into that computer. So you have to buy license for your target customer. And if there are some software that cost really, really expensive.
Yeah.
And if you did that, then your system is going to be way more expensive, right? So this is pretty capable, but it's not going to cost an arm and a leg, so to speak. So there are a lot of advantage of using it. I have been using it for long time. I think first I was exposed to, they used to call it HPV.
Okay.
And yeah, so I had that HPV back in 80s. So,
Okay.
but let's stop recording for now.
No worries.
But so that see, LabVIEW is way more used than HPV or now Agile and Keysight V. So this is kind of a professional grade.
Yeah.
And
both seem similar. When I used LabVIEW in the past, the Keysight technology software V seems similar.
Yeah, V is way more professional grade, as I said, and I will run some V example down the road, as well as the image example down the road, so that you get a better feeling about. I want to give you in other words, let's say tomorrow, and again, don't hold me on this thing. I'm just thinking. Tomorrow, if some party calls me, Anis, I need a system, but I also need someone to run it. I don't have one. We got to be ready for that, right? So,
Sure.
and also hopefully you can find some interested parties in your neck of the world, would and universities and whoever. That way, there are a lot of potential there. It's how should I say? This is just the beginning,
Yeah, I liked the seashell example. It was relatable to biologists, geochemists, geologists.
Yeah.
And relatable to the common person or just an everyday person.
Yeah.
Children talk about tree rings. Somebody speaks about lunar cycles affecting tides. It was good.
Yeah. Well, I'm gonna share I have a little write-up it's a technical newsletter, right? So I'm gonna share that with you, with all of you. And I'll do that very soon.
All right, thank you.
But again, don't hesitate to ask questions. These questions could have been part of our recorded program, and that would have been just appropriate because other people would have the same. When we eventually we'll upload it. we haven't done that yet, but we'll make a channel, and then other people will have a way to think, what to think.
All right. See you next week.
See you then. You have a wonderful weekend, and feel free to go through the material I'm going to be sending and bring it into the discussion, or if you have any other comments.
All right. Thank you.
Okay. Bye now.